Hello there. I'm about to start this lecture, and when this lecture starts, I'm going to tell you that the exam is coming up that's going to be on February 8th, and I'm going to tell you it's on Tuesday. It's not on Tuesday, it's on Monday. So ignore that part when I tell you it's Tuesday because it's really Monday. All right? I'll start the lecture in just a second. Okay, welcome back. Today we're going to be continuing with our two-dimensional kinematic equations. We started looking at two-dimensional stuff last time. We're just going to continue with it today, primarily looking at examples of the same sorts of equations that we did last time. A couple things just let me mention. First of all, don't forget our first exam is coming up. It's going to be on Tuesday, February 8th. It will cover sections 1 through 3, meaning it will cover what we do up through today. What we do next time will not be on this exam, but will be on the next exam. You may use, don't forget, one side of one 4x6 inch file card. You can put whatever you want on one side. Don't put anything on the second side. All right, now one quick thing. Let's remember. First of all, let's keep in mind the procedure that we're going to follow for solving these problems. The first thing we're going to do, draw a picture. Second thing, list the variables. Third thing, determine the values for the variables after we've chosen an origin for our coordinate system. Determine what we need, what do we have, what we're looking for, what do we have, what do we not have, what do we want, what are we looking for, that sort of thing. Then solve the equations, and then always think about the answers that you get. Ask yourself, do these answers make sense? Okay, now one thing to keep in mind, let's just think about vectors just for a second. Let's imagine we've got our standard orientation for coordinates, say x positive to the right, y positive upwards. If we've got some vector, let's say a velocity vector or something like that, maybe some velocity that is actually maybe in that direction. Let's imagine that our velocity maybe has a magnitude of, let's say, 30 meters per second and is maybe at an angle of, let's say in this case, 25 degrees to the left of the y-axis. Well, what are the components of our velocity? Remember, we always need the components to use in our equations, and I've got our 8 kinematic equations over here, our 4 x components, our 4 y components. So what are the components of our velocity vector here? Well, we break these down like this. Here, this is the x component, Vx, this is the y component, Vy. In this case, Vx will be the opposite side to the angle, so this will be 30 meters per second, sine 25 degrees. But let's notice this component is actually pointing to the left. It's going to have a negative x component, so we actually have to put in a negative sign there. The y component, Vy, that's going to be the adjacent side to the 25 degrees. So this is going to be 30 meters per second cosine 25 degrees. It is in the positive y direction, so that will be positive. We multiply this out, and what do we get? Something like negative 12.7 meters per second and 27.2 meters per second. So there are the components for the vector. So keep in mind, you do not necessarily always have vectors pointing in the first quadrant. Sometimes you might have negative components, and you have to watch and look at the direction of those vectors to determine whether you're going to have a positive or negative component. All right, so let's look at some problems. Let's continue with some two-dimensional kinematic problems. And these are written up in your notes, so I'll refer to the same problems that we've got listed in your notes. So, the first one. Let's imagine that a tennis ball is hit horizontally at 28.0 meters per second. It lands on the ground 19.6 meters away from the person who hit it. How high above the ground was it hit? Okay, so there's the problem. What's the first thing we do? We draw a diagram. So, here we go. Draw a diagram. Remember, this does not have to be a good diagram. Here's our ball. It is hit horizontally. So, we know it's going to be hit like that. Qualitatively, what do we expect the motion to look like? Well, we expect the motion to look something like this, come over and hit the ground over here. Here's our initial point. Here's our final point. What do we know? Well, it is hit at 28.0 meters per second. So this is 28.0 meters per second. It lands on the ground 19.6 meters away. So this is 19.6 meters. And we're looking for how high above the ground was it hit. So we're looking for that. Okay, so there we go. Now what do? Write down our variables. Let's always remember, try and write these down in the same order so it'll help us remember. So we've got x naught x, vx naught, vx, ax. Whoops, ax. Y naught y, vy naught vy, ay, and t. Now let's choose our origin. We can put our origin any way we want. Typically, as I said, usually the lowest point and leftmost point is typically the easiest point. So we'll choose the point below the ball, directly below the ball. Let's just say that to the right is positive and upward is positive. So left positive to the right, y positive upward. Now, what values do we know for our variables? Let's think about this. Do we know x naught? Remember, the initial point is here. Final point down here. Initial, do we know the initial x value? What's the x coordinate initially? Yeah, we know that, it's 0. Do we know y naught? Do we know the initial y value? That's how high it is? No, we don't know that. What about x? Final horizontal position? Well, that's over here. Yeah, well, that'll be 19.6 meters. What about y? Well, we know the ball is hitting the ground. So what is the final height of the ball? Well, we know that that is 0. All right, Vx naught, the initial velocity in the x direction. Well, initially the ball is hit horizontally. So what is the x component of that? What's the initial x component of the velocity? Well, it's the whole thing, 28.0 meters per second. What is the initial y component of the velocity? Well, it is hit horizontally. Is it going up or down at all initially? Just as soon as it's hit? No, it's going horizontally, so we know that that is 0. What about Vx? Well, when it hits the ground over here, it's going to be going in some direction like that. Do we know what the horizontal component of the velocity is? Well, not right off the bat. So we'll say we don't know it. Vy, likewise, we don't know what the y component is, so we'll leave those. Acceleration in the x direction. Well, what is the acceleration? For any problem like this, the acceleration is always going to be the acceleration due to gravity. Typically, it will say ignore air resistance, but in a problem like this, even if it doesn't, we need to assume to ignore air resistance. So, what's our acceleration in the x direction? Well, it's 0. What's the acceleration in the y direction? The acceleration is due to gravity. It's downward. We said that upward is positive, so downward is negative, so the acceleration in the y direction will be negative 9.80 meters per second squared. All right, there we go. So there, and t, do we know t? No, we don't know t. There we go. That's everything we know. What are we looking for? The problem asks, how high above the ground was it hit? So what are we looking for? We're looking for this height. What's that? That's the height that it is initially. That'll be y naught. So we are looking for the value of y naught. So how are we going to go about solving this problem? Well, we've done enough of these that you might be able to guess. We're going to use, we could go directly to the equations, and I would suggest if you have trouble figuring this out, you might do that. Go to the equations, look at each equation. Does it have what you want? You know what, this is our first one. Why don't we go ahead and do that? Let's see, we want to find an equation that has a y naught in it, and we know everything else. So let's just see if we can find that. Any y naught here? No, so we can't use it. No y naught, no y naught, no y naught. So we cannot use the x components to solve for y naught. Is there a y naught here? No, no y naught. Is there one here? Yeah, there's one here. Do we know everything else? Well, we don't know what Vy is. We do not know what Vy is, so we cannot solve this equation for y naught unless we know everything else. Nor do we know t. We don't know what t is either, so we can't use that. This one's got a y naught in it. Can we solve for y naught? Well, we know everything else here. except for t, we don't know t, so no, we cannot solve for y naught. What about this one? Well, let's think about this one. We've got a y naught in it, but, oh, again, vy, we don't know what vy is, so we cannot use that one for y naught. So there's nothing we could do, but you might remember the kind of approach that we use is let's use the x motion, solve for t, because we know if we had t in some of these, we could solve for y naught. So let's solve for t, then come back and solve for y naught. So what here can we use to solve for t? The first one, well, we don't know Vx, but if we put in Ax is 0 here, we do see that Vx is equal to V naught x. So actually, using the first one, we could say that Vx is 28.0 meters per second. So we actually can solve for Vx using the first one, but that doesn't get us t. What about the second one? Well, we know everything now that we know Vx. We do know everything in there except for t. We could use that, but we'd have to use the value for Vx. That's possible. Number 3, we could do that. Number 4, it doesn't have a t in it. So let's use the third equation. We'll solve that for t and then solve for V naught. So, third x equation, what do we have? X equals x naught plus V naught x t plus 1/2 ax t squared. X naught, 0. Ax, 0. So we have x equals V naught xt, or t equals x over V naught x. X is 19.6 meters divided by V naught x, 28.0 meters per second. Divide that out, and we find that t is equal to 0.700 seconds. Excuse me. Now we go to the y motion. Why don't we use the third equation here? Solve for y naught. We've got y equals y naught plus v naught y t plus 1/2 a y t squared. We have that y is 0, v naught y, or vy naught, either one is 0. So we have y naught equals negative 1/2 ay t squared, or negative 1/2 ay is negative 9.80 meters per second squared times t squared, 0.700 seconds squared, and that gives us y naught equals, multiplying this out, notice we have negative of a negative, which gives us a positive final value, which is what we would expect. That makes sense. We expect to have a positive initial value there. Multiply that out, and we find y naught is 2.40 meters. All right, does that sound like a reasonable result for hitting a tennis ball? Yeah, that doesn't sound too bad. Okay, so, excuse me, very, very good. We were able to go right through it. Again, draw a diagram, write down your variables, write down the values for your variables, look at your equations, go through, solve, find your answer, ask yourself, does that seem like a reasonable result? Okay, very good. Let's try another one. A golf ball rolls off a horizontal cliff with an initial speed of 11.4 meters per second below the horizontal. The ball falls a vertical distance of 15.5 meters into a lake below. A, how much time does the ball spend in the air? What is the velocity of the ball just before it strikes the water? So, what do we do first? Draw a diagram. So, here's a cliff. Comes down, the ball comes off the edge at an angle of 15 degrees below the horizontal, with a speed of 11.4 meters per second. Qualitatively, what's this motion going to look like, do we expect? Well, it's coming off the cliff. And we expect it to do something like that, hitting the ground over there. We know that it falls a vertical distance of 15.5 meters. So we know vertically this is 15.5 meters. And then the question is, how much time does the ball spend in the air, and what is the velocity of the ball just before it strikes the water? Okay, so let's draw our coordinate system. Where do we want to put our origin? Excuse me. Sorry. Let's put our origin at the leftmost lowest point. So we'll put it down here at the bottom of the cliff. X positive to the right, Y positive upwards. Let's write down our variables. Let's write them over here. Again, let's write them in order. X naught X, Vx naught Vx, Ax, Y naught Y, Vy naught Vy, Ay, T. Okay, what do we know? X naught, well, the ball is initially above our coordinate system, so X naught is 0. Y naught, well, now remember this is the initial point up here, final point here. Y naught, the initial height, that'll be 15.5 meters. X, the final horizontal distance, well, no, we don't know that. Y, the final height, well, it's hitting the ground on the axis, so we know Y is going to be 0. Vx naught, Vy naught, well, we need to take our initial velocity and we need to break it down into components, so let's do that. We have a magnitude of 11.4 meters per second at an angle. Vx naught, the x component, and Vy naught, or Vx naught or V naught x, it doesn't matter. They mean the same thing. Vy naught, V naught y, same thing. All right, so Vx, that's going to be the adjacent side. So we'll have Vx naught equals 11.4 meters per second. The adjacent side is cosine 15 degrees. While the y component, Vy naught, that's the opposite side. That'll be 11.4 meters per second sine 15 degrees. But let's notice the vector points to the right, so the x component will be positive, but it points down, so the y component will be negative. All right, there we go. We multiply that out, and we get Vx naught is going to be 11.0 meters per second. Vy naught will be negative 2.95 meters per second. So we can add that in for our variables. We've got Vx naught is 11.0 meters per second. Vy naught negative 2.95 meters per second. Okay, Vx, what's the horizontal final velocity? Well, we don't know that, but you might be able to guess we're going to have a 0 horizontal acceleration. So from our first equation in the x motion, we can kind of assume right away that the final x velocity will be the same as the initial 11.0 meters per second. Vy, we don't know what the final final vertical component of the velocity is. Ay, again, what is the acceleration for this motion? It's the acceleration due to gravity. That's going to be 9.80 meters per second squared downward. We defined upward as positive, so that will be negative. So Ay will be negative 9.80 meters per second squared. And T, we don't know that. All right. Now, what are we looking for? Back to the problem. Part A, how much time does the ball spend in the air? Well, how much time? What's that? Well, that's T. So we're looking for T. And part B, what is the velocity of the ball just before it strikes the water? So what's the final velocity? Well, the velocity vector, well, how do we find that? Well, we'll need Vx and we'll need Vy. We'll actually need to solve for Vy and then put it together with Vx to find the final velocity vector. All right, there we go. So we need to solve for T, we need to solve for Vy. Let's look at the equations. Can we use this one? Well, no, we actually use that multiplying by Ax is 0 to solve for Vx, so we can't do that. Can we use this one to solve for T? Or Vy, well, it doesn't have a Vy in it. Could we use it to solve for t? Well, we don't know x, so we can't solve that for t without x. Likewise, can't solve that for t without x. What about part 4? No, it doesn't even have a t in it. So let's come down. Here, can we solve this for Vy? Well, we don't have a t. Can we solve this for Vy? Again, we don't have t. Could we solve this for Vy or t? Well, yeah, it doesn't have a Vy, but we could solve that for t, and we know everything else. So we could solve that for t. What about this one? Could we solve this for Vy? Let's see. Actually, we could solve that for Vy. We could solve equation number 4 and solve that for Vy, or we could solve equation number 3 for t. Why don't we go ahead and do that? We'll solve equation 3 for t. Now, we've all got this, I hope, so I'm going to erase this. And let's look at equation number 3. So what do we have? We've got y equals y naught plus v naught y t plus 1/2 ay t squared. We've got that y is equal to 0. And so we can put our values in. 0 equals y naught, 15.5 meters, plus v naught y. V naught y is negative 2.95 meters per second t, plus 1/2 ay, which is negative 9.80 meters per second squared, times t squared. And we've got to solve that for t. Well, that looks like a quadratic. Let's put that into our standard form. This is going to be negative, so let's bring everything to the other side. That'll make our coefficient of the squared term positive. So 1/2 times that is 4.9. Bring it over here. Positive 4.90 meters per second squared t squared. Got a negative here. Bring it over here. It'll be positive 2.95 meters per second t. Got a positive here. Bring it over here. Will be negative 15.5 meters. All of that equals 0. So let's solve that for t. What do we get? Putting in the quadratic, we'll get t equals the opposite of b, negative 2.95 meters per second, plus or minus square root of b squared, so 2.95 meters per second squared, minus 4a, a is 4.90 meters per second squared, times c, c is negative 15.5 meters. All of that is under the square root, and all of it is divided by 2 times a, or 2 times 4.90 meters per second squared.